Hello everyone. Hello guys. It's great to see you guys joining in early. Please stay tuned. We'll be starting shortly. Also, on behalf of the audience, I welcome Sir Mr. Nils. Hello everyone, welcome to another session of DataHour series. We will start in 5 minutes. Till then, let's get to know each other in the chat section. Hello guys, am I audible? Can you please reply in the section? Okay, chat is disabled. Wait a minute, let me on it. Enable it. In the meanwhile, guys, I'm going to launch a poll. I ask everyone to please participate in the poll. Hello, sir.
Hello, can you hear
Hi,
me?
sir. Yes, sir, you're audible. Thank you for joining us, sir.
Yeah, looking forward to it.
Yes. Hi guys, I have launched a poll. Please participate in the poll. In the meanwhile, I'll look into the chat section. Sir, we'll start in 5 minutes, sir.
Sounds good.
Yes. Hi guys, the chat section has been enabled. Hi. Can I see few messages from the participants? Hi, Meenakshi Devi. Hello, Akshay. Hi, Krishna. Please, some of you messaging to host and panelists, please make it to everyone. Hello, Anushman. Yeah, now you are messaging to everyone. Yes, Anushman. Hi, Hang Young. Sorry if I'm pronouncing it wrong. Hi, Sandeep. Hi, Anjana. Hi, Abhay. Hello from US. It's great. Hi, Srinivasan. Okay, let's get started. Okay. So welcome everyone to another session in the DataHour series. We are also thrilled to be here with you this evening for a session full of action-packed learning. I am Tamil Selvan Murugesan, part of the data science team at Analytics Vidhya, and I will be moderator for this session. For those of who have you joined for the first time, let me give you a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun one to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. Okay, now on to our session today, which is improving search results with semantic search. So about semantic search, pre-trained transformer models have significantly improved search results and yield much better results even with the absence of linking information like PageRank or click rates. This is especially beneficial for use cases where such information is not available. So in this DataHour, Mr. Nils will cover the basics of semantic search and how to integrate it into systems to yield a better search experience to users. So I hope you are excited to attend this DataHour with us. So before we kick off things and hand it over to our speaker, a quick recap of the housekeeping things. We are recording this session and we'll make the recording available in a few days on our YouTube channel. Please use the question and answers section for asking any questions you might have during the session, and we'll do our best to answer them as the DataHour progresses or towards the end. Also, we'll share a poll about the feedback of the session towards the end of the session, which I request you to kindly fill up. Now on to our speaker. In this session of DataHour, we have Mr. Nils with us. So Nils is an expert on search relevance using pre-trained transformer networks. In 2018, he authored and open sourced the popular sentence transformers library, which is the most popular framework to design semantic search applications. Recently, he joined Cohere.ai as principal scientist to lead the search as a service team to develop new state-of-the-art neural search models and to make them broadly accessible as API endpoints. Over to you, sir. The virtual stage is all yours, and also forgive me, sir, if I pronounced your name wrong.
Great, thank you so much for the introduction.
Yes.
So if you could enable screen share for me, then I can start with the presentation. Okay. So you can see my screen? Great.
Sir, you are good to go.
Okay, great. So yeah, I'm really happy to be here. And yeah, so today I will talk about improving search with semantic search. So I work for Cohere.ai. Cohere.ai is a Canadian company focusing on large language model and providing them as an API. So we train state-of-the-art models in terms of embeddings and generation. And not only training these models is difficult, but also when you go to like 100 billions of parameters, it can become quite complex to host them and to run inference on this. So we also specifically optimize them so that everyone can use them based on a pay-as-you-go API, which allows you to use these models in a really simple and efficient way, and also with like little upfront costs. So you can just, so sometimes you just pay pennies to use like state-of-the-art search functions, and you can build like really interesting, nice prototypes on it, and then see if you get like traction in the market. And if you see there's like some use case for your application, you can also nicely adapt them specifically for your task and build amazing applications on top of it. So as mentioned today, I want to talk about neural search, and maybe sometimes it's also called semantic search. So that's the terminology is not really clear. But if you have heard about it, there's kind of a hype about it. Like a lot of people talk about semantic search, neural search. And you always should question yourself, is the hype really justified, or is it just a hype? And what I like to provide here is a real example. So this is an example on the simple Wikipedia. It has like 170,000 documents. And the query you're searching for is like really simple. What is the capital of the United States? And if you use lexical search BM25, so BM25 is the best lexical search algorithm. It was like the state-of-the-art method for like 20 years in the field. Everyone is using it. Elasticsearch is heavily built on top of it. But for this really simple search query on what's the capital of the United States, the top 3 results are totally disappointing. So the first result is on capital punishment, because it contains the words capital, it contains the words United States. Second search result is on Ohio, because Ohio is a state in the United States. It also has a capital. And the third search entry is about Nevada, because it's also a state in the United States. It has a capital. So on a lexical match, these results look good, but they are completely useless for any human. And probably everyone has experienced this if you search in Outlook or in Word or somewhere in your internal systems. The search results are really, really bad. And we're totally not really happy with the search results. So Google, they were able to solve it, but Google, what they did is they used like other information you have on the web. So first information they used is PageRank, so put more important pages higher in the search results. And the second information they used is like from the billion user base, they used like click rates, interaction data, so they know how long are you on every website, how long do you read it, do you interact with the website, and this also allows them to get a judgment how good is the content of certain websites. But in many scenarios, you don't have this information. So if I search in my email inbox in Outlook, there are not a billion users searching in my inbox. It's just one user, it's me. I also don't have a PageRank, so I need some other solution, some solution that works really well just reading the text. And semantic search or neural search is able to do it. So if I take a neural search engine, so it's an engine that is based on neural networks, and I type in the same question, my first result is about Washington, DC. So that's what I was looking for. So perfect hit on the first place. Second entry is also kind of reasonable, like it's defined, it gives a definition, what is a capital city? And the third entry is about the United States Capitol, because maybe I misspelled capital and capital, so it gives me also an alternative. Maybe I was looking for what's the capital of the United States. You can not only put this into like an example, into like a cherry-picked example, but you can also put like hard numbers on it. So this is a data set, a benchmark from 2004. So it's like really old, so 16 years old, or 18 years even old. And over the years, we see different systems, how well they perform on this benchmark. So the black line here, this solid black line is the best systems from 2004. So that's 18 years ago. And as you see over the years, there was like not really any progress over the last 20 years. So systems from 2018 are as good as systems from 2004. And it only changed once the pre-trained transformers entered the field. So in 2019, the first papers appeared how to use a pre-trained transformer, specifically the BERT network, to do search. Then we saw like some nice improvement in 2020. And also in 21 and 22, we see a lot of improvement. And now we get like, we know how we can search on text and get the results you're looking for without relying on a billion-based user bases or on PageRank information that tells you which documents are relevant and which documents are not relevant. So today I want to talk about like different architectures. So there's not a single architecture where you say, okay, this is the one architecture you should use for search. So it's with lexical search, it's kind of easy. Use BM25 and this works well. But with neural search, there are like different types of architecture. Each has pros and cons. And to understand them well helps you a lot to improve the search result the most. And also there are like nice combinations of these search architectures where you can balance the pros and cons of individual architectures. So I will talk about doc-to-query, I will talk about cross-encoder, and I will talk about biencoders, how they work in principle, and what are the pros and cons of these different architectures. There are many more architectures available if you dive into neural search, but I think these are the three most important architectures to know. The first architecture from 2019 is doc-to-query. The idea is kind of nice and interesting. So you have some documents. So in your document collection, for example, a document about research of finding that cinnamon reduced blood sugar levels naturally when taken daily. And then you have an encoder-decoder model that tries to predict what are users searching for if they want to read this document? So for example, a user might search for, does cinnamon lower blood sugar? And you run this encoder-decoder model on all the documents you have in your collection. So for all documents, you predict what are queries the user could search for. And then you do a simple like string concatenation. You take the original document, you take all these predicted queries from your model, and you index this in a normal search engine like Elasticsearch, OpenSearch, Solr, Lucene, whatever. And then you can do just simple lexical search on it. So the lexical search not only search in the original document, but also searches in the predicted queries, and you get like better retrieved results. So this is like a really simple approach. You can plug it into any existing search architecture you have. You just predict the queries, you add it to the text, and then you get better results. Different architecture is called cross-encoders. So this is basically a learning to rank method. So you have your first stage retrieval. So you have, for example, lexical search, which takes the search query, looks in your document collection of hundreds of millions documents, and then you get like 1,100, whatever number of candidates. And then you pass these candidates to a re-ranker, also called cross-encoder. And the cross-encoder, you take the query and the document, you concatenate these two, and the BERT network predicts a score between 0 and 1, how relevant is the query for the given document. You do these for all the 1,000 documents you got from the first stage retrieval, and then you re-rank based on the score the BERT network predicted, like how relevant is the document for the given query. Third architecture is on biencoders. Later, I will also go more into details on the different architectures to explain more pros and cons and how they work. So the third architecture is on biencoders, which uses dense vector spaces. So you have a method that takes all your documents and you encode them in a vector space. So here it's like a 2-dimensional vector space, but in reality, it would be a 1,000-dimensional vector space. And then a query comes, you also project this query in the vector space, and then you check what are the nearest neighbors in this vector space. And the nearest neighbors, you hope that these are the relevant documents. So for example, the query is like, what's the capital of the United States? And this document is Washington, DC is the capital of the United States. And then you can retrieve this document for the query. In terms of network architecture, it's straightforward. So it's called biencoder because you have like independent encoders, so independent flow for querying document. So you pass your document to a transformer network like BERT. You have some pooling operations. So for example, you take the mean of the contextualized word embeddings from BERT, and then you get the vector representation. So fixed size vector representation, typically something like 500 to 1,000 dimension. And you can do the same with the query, and then you have a similarity computation. that tells you how similar is the query to the document, or in a vector space, how distant, how close is the query to the document. This also works nicely not only on language, but it can also work multimodal. So, for example, you have a large collection of images. You encode the images in a vector space, and then you have like some text, like 2 dogs in the snow. And then you check what is the closest image for this text. And then it retrieves images that are relevant or matching to this query. And it also works in a multilingual setting. So it doesn't matter if you input this in English or in German or in Chinese or in Hindi or in Spanish or in French. They can all be projected to roughly the same spot in the vector space. Then independent how you search for 2 dogs in the snow, you still get the same image. So you can build really quickly a multilingual search engine for images or for video or for audio. So these methods are kind of generic. So there, in terms of bioencoders, you can differentiate between dense and sparse bioencoders. So dense bioencoders, they work in a dense vector space. So they output, for example, when you take a bird network, a 784-dimensional vector space. And dense means that all of these 784 dimensions have some non-zero values, some positive, some negative value. And the advantage compared to lexical search of these approaches is that they can overcome the lexical gap. So in lexical search, if you search for US, USA, United States, these are considered different terms. So if I search for what's the capital of the US, I will not find documents talking about United States. They can also respect the word order. So if I search for how to get a visa from Germany to Canada or how to get a visa from Canada to Germany, for lexical search, it's the same. So it can respect the word order, but for dense embedding models, they can respect the word order. So they know for the first search query, I need to retrieve other documents than for the second search query. And these approaches can also know about related terms. So for example, I search for how can I compute Spearman correlation with NumPy, but there's no function in NumPy to compute the Spearman correlation, but there is a function in SciPy to do it. And then it retrieves the document and says, here's how you can compute Spearman correlation in SciPy, because the model knows that NumPy and SciPy are kind of similar frameworks which can often be used interchangeably. Recently, over the last year or so, sparse bioencoders became popular. So it's still more in a research phase, sparse bioencoders. So the infrastructure on them is still a bit lacking, but they show really promising characteristics. So a sparse bioencoder works that you also take the query, you pass it through the transformer network like BERT, and then you have a projection to, for example, 30,000 dimensions. So you go from 700 something dimensions to like 30,000 or more dimensions. But it's a sparse vector. So most of the entries are 0 and only few of the entries have a non-zero value. And one common approach is to use the BERT tokenizer size. So you project it to the different word pieces of the BERT network. And if you have a query like how to learn Python, it will create like a sparse representation about Python. So the document should talk about Python. So this has a relevancy of 2.7. Should also mention guide, because if I want to learn Python and the website is talking about this as a guide about Python, that's also kind of relevant. Also has learn and teach as kind of high relevancy terms, but also sometimes like these curly brackets. So the model says, okay, the document should also contain a curly bracket. That's also a really good sign about learning Python, which is harder to explain why the model thinks that a curly bracket is really relevant here. So this is like really hard to interpret. At the end, the sparse representation, it's a back of word approach. So a flight London to Paris and flight Paris to London would have the same representation or really similar representation. So they are, that's like a weakness of these sparse bioencoders, which you don't have when you work with a dense bioencoder. So how do you train these representation models? There are different ways, different loss functions. The one that's most commonly used and works the best has many names. I personally call it multiple negative ranking loss, but sometimes people call it also training with in-batch negatives or info-NCE or NT-cross entropy loss, but it's always the same loss. So the idea is you have like some positives. So some text where you say these should be closed in the vector space. So this can be a query and the answer, or it can be a question and a duplicate question. So maybe in an online community, people annotate a duplicate question, or it can be a paper title and another paper cites, and you assume, okay, if two papers are citing each other, they should be closed in the vector space. And then you have like this pair which should be close in the vector space, and then all the other pairs should be distant in the vector space from a batch. And you can compute it really similar to like cross entropy loss. So you compute what's the similarity between the positive pair AI and PI, and then you compute what's the similarity between all the other pairs. And as similarity functions, you can use cosine similarity or dot product. So to give a bit more intuitive explanation, the loss function works kind of similar to a multiple choice test you have like in school. So for example, you have the question, how many people live in Berlin? And then there are like 3 answer options. Around 3.5 million people live in Berlin. Washington, DC is the capital of the US. And the 2021 Olympics are held in Japan. And then the model goes, it encodes the A, which stands for anchor, and the P for positives in the vector space. So for example, between A1 and P1, you get a similarity of 0.5, 0.3, and 0.1 for the others. And then you use cross entropy loss. So you have your predictions of these 3 candidates, 0.5, 0.3, 0.1. The labeled data tells us, okay, A1 and P1, that's the correct answer. And then you do cross entropy loss based on the prediction versus the gold label. So really similar how you do a standard training of a neural network for classification. So in a batch, you do not have like only a single question and like 3 different answers, but you have like these pairs. So you have like A1 and P1, like how many people live in Berlin, 3.5 million people live in Berlin. Second one is what's the capital of the US and where are the Olympics this year? And then you compute all the vectors for all the A's and all the vectors for all the P's, and you do all the similarity combinations. So you get like 3 times 3 possible combinations, and then you can see it as a classification task. So A1 should match, should be close, should have a high similarity with P1. A2 should have a high similarity with P2, and A3 with P3. So you say your gold label is like this diagonal matrix where you say A1 and P1 and A1, A2 and P2 and so on should have a high similarity. And for all the others, it should have like no or low similarity. Implementing this, it's not so difficult. So it's rather straightforward. So here's a function in PyTorch. So you have all the embeddings for A's, all the embeddings for your candidates. You compute your similarity function, and maybe you scale this similarity function by some value. And then you say, okay, my labels, it's the, you say, okay, AI should match with BI, and then you compute the cross entropy loss. So it's like 3 lines of code, how you can implement such a function. What's more interesting is how can you get like better models? So how can you get a really, really good model that works extremely well for in this vector space, so which is extremely well in search. This most simple trick is to increase your batch size. So as we see here on the x-axis, that's the best batch size. On the y-axis, it's the performance. So how well does the model perform for search? And the black line is like the presented approach. And as we see, if we go from 128 batch size to like 8,000, the performance constantly improves. And it's similar to like a multiple choice test in school. So if you have like few candidates, few answers, so you have a question, 4 answers, it's kind of easy to guess it right by chance. But the more answer candidates you have, the more difficult is it to get the correct answer, and the better test if you actually know the answer to the question. The other technique to significantly improve the performance is to use hard negatives. So that's the red line. So hard negatives is you include in the training hard answers. So like in a multiple choice test, you add possible answers which sound really similar to the correct answer, but which are still wrong. So how do you do this for a neural network? So you go away from pairs and you go to triplets. So now you have like triplets of an anchor, a positive, and a negative. And the negative should be similar to the anchor, to the A, but it should not match with the A. And in the vector space, you say, okay, this is my anchor. I want this single positive to be close in the vector space. And I want all the other P's and all the other N's to be distant in the vector space. Getting this hard negative is not so easy because it must be a negative. So for example, a bad example would be how many people live in London. And then you say about 9 million people live in London. That's the correct answer. And then somehow as negative, you say London has a population of 9 million people. So the model would try to get A and P close in the vector space, but at the same time would try to get A and N distant in the vector space. So this would extremely confuse the model. Similar to students, they would be confused. So why is this a correct answer and why is this an incorrect answer? Better example, real hard negative would be around 1 million people live in Birmingham, second to London. So this is kind of similar to P. It talks about people living in cities in UK, it talks about London, but this is not the correct answer. That's not the answer for the question. So this would be a really good example. The challenge is how do you get these hard negatives? So how do you get them at scale, like for 100 millions of training pairs? And how do you ensure that you don't have like any bad examples in your triplets? So one strategy is you exploit some structure in your data. So for example, in a citation graph, you can say, okay, I want to have the title and the cited paper title be close in the vector space because I assume they're similar. And you say, and then you take a paper that's cited by the cited paper. So it's like 2 hops between like the original paper. You say, okay, this is like less similar. Or in Q&A, you could say, I take the answer, and then I take an answer with fewer stars or upvotes as a negative. Second strategy is to mine hard negatives. So you can use BM25, for example, lexical search to find the top 100 most similar text to the anchor or the positive. And then you select one of these randomly. But there you have to make sure that these are actually negatives so that you don't get another positive as your hard negative. You can also improve your quality with better batches. So always when we train these models, we think about like what's really good data loading strategy. And a lot of time we spend on writing the data loading and creating the batches, because this has like a really big impact on the performance. So assume you have question and answers from Stack Exchange. There are like 140 different subforums on like Stack Overflow, everyone knows. Then there are also subforums on traveling, on cooking, and so on. And if you randomly sample question answer pairs from Stack Exchange, you can get a batch like one question about Python with the answer, one question about the travel with the answer, and one question how to cook pasta with the answer. And here for the model, it's really simple to find the right answer. So as similar as in school, for a student, it would be really simple in a multiple choice test to find the correct Python answer to this Python question, because you just take the one answer that talks about Python. A better approach would be that you sample pairs from one subforum. So for example, Stack Overflow. So in the batch, you have a question about Python, Java, and C with their respective answers. So it's not only sufficient for the student to know, okay, this also talks about programming, but it would also need to know, okay, which of these answers talks about Python. But still, it does not really need to know, does the answer actually answer the question the user asked about Python. So an even better approach is that you sample pairs from similar tags. So for example, in Stack Overflow, you take the Python tag, and then you have a batch, one ask about Python, one question about NumPy, and one question asked about pandas. And then the student, the model really needs to know, okay, is this the right answer to the Python question? Because also all the other answers in the batch also talk about Python. So it really needs to create a deep understanding of the text to actually be able to match which questions matches which answers. But there you have to be sometimes careful. So if you only have these hard batches, it can be that vector space start to overlap. So for example, that the Stack Overflow vector space about programming questions overlap with the questions from the travel forum. Because it never has seen a travel question and a programming question in the same batch. So it was never required to like separate these vector spaces. So it can make sense to include like 90% difficult batches and to have like 10% easy random batches so that the model clearly sees, okay, this like different topic should be really far away in the vector space. A big challenge for dense vector spaces are unknown words. So if you follow the transformer architectures, people became really creative in naming things. So it started with Elmo and Bird, and then a recent model was called like Big Bird Pegasus. And the challenge is a model might have never seen this word. So it takes the word, passes through the dense encoder, and then it forces into like a low dimensional vector space. And should this Big Bird Pegasus be close like to bathroom or to sprinkler or to microwave? So it has to be put somewhere in this dense vector space without knowing what the word means. And if you do this, if you check, the closest word means in the vector space are big boss, big data, and big ass. So if someone searches, how can I load a Big Bird Pegasus model, and might find documents talking about big boss. So this is like a severe limitations of dense bioencoder models. In contrast, sparse encoders, they work much better on unknown words. So it works with the Bird word piece tokenizer. So it splits the query in word pieces and then assigns weights for the word pieces like Big Bird Pegasus. So it says, okay, I have no idea what this means, but it looks kind of relevant. So I just split it into word pieces and then do a lexical search based on these word pieces. And then it also tries to add some related terms. So for example, bird and birds and big and giant also assign some relevancy. So this sparse encoder works much better than dense bioencoders in terms of like unknown words, which can happen as soon as language develops, new companies are founded. And yeah, so sadly, or luckily, however you see it, our language can or constantly evolves. So we have seen that there was like Big Bird Pegasus, but there's also like Klexchain, some cryptocurrency. There's Forward, a company from Israel, where this is the hexadecimal code, which is associated with the Windows activation key. And this is for like dense embedding models, really hard to put in the vector space. So it sees this random string on hexadecimal and does not know how that is associated with Windows and activation key and registration. Just put it somewhere in some strange place in the vector space, which can yield really bad search results if you search how to fix this error code. And here the sparse encoders works much nicer by splitting it into the word pieces and does a lexical search as soon as it does not know a certain term. Big challenge still remains like synonyms and related terms. So for example, a lot of the models, like BERT model, has been trained on data from 2017, 2018, and also fine-tuned on 2018. So it has like no idea about coronavirus, that it's linked to COVID-19 and SARS-CoV-2. So if you check how is COVID-19 transmitted, it will not find any documents talking about coronavirus or SARS-CoV-2. Similar, if you have a question, which vision transformer model is the best, and then you have a new acronym like VID, which stands for Vision Transformer, does not know that this acronym is connected to Vision Transformer. So, and this is still a really big challenge. How can we update our models to incorporate new knowledge, new things, new companies, new product names, so that search really works well on these new type of language, which you have not seen in pre-training or in fine-tuning. We wanted to test it a bit more systematically. How well do different neural search architectures work on out-of-domain performance? So they were trained on one data set, on a public data set from Microsoft Bing, on search queries from the Bing engine. And then we tested it on a lot of tasks and a lot of data sets from different domains. So for example, on Signal 1M, the search query is a news headline, so some news article, and you want to find tweets talking about this news event. And we wanted to see how well do these different approaches work in neural search. And first, we were kind of surprised that the dense embedding approaches perform really badly out of domain. So in domain, so before that paper, everyone was just evaluating in domain. So they had like a lot of training data. And there we saw like a big improvement, like 18 points in DCG at 10, better than lexical search with BM25. But as soon as you switch to a different domain, like BioAsk is on biomedical publications, SciDocs is on general scientific publications, you see that semantic search with this type of model is actually worse than the baseline, the lexical search we used for like 20 years. And on these 18 data sets, BM25 was better on 10 out of 18 data sets. We saw big differences in terms of the architectures. How well do they perform compared to BM25? So the best architecture, which was better on 16 out of 18 data sets, was BM25 plus a cross-encoder, and also the doc-T5 query. So that's a doc-to-query using the T5 system, was also better on 11 out of 7 data sets. But then the other architectures, they often performed kind of poorly. So for example, the dense passage retrieval model from Facebook just performed well on the one Wikipedia datasets, but for all other datasets, it performed worse than simple lexical search. Sparse embeddings, they work much better for unknown domains. So sadly, it's not included here in the graph, but these sparse embeddings, they are better on 12 out of 13 data sets. So the authors tested it on 13 out of 18 data sets, and there it was better than on 12 data sets than lexical search, because it has this nice capability that it can deal well with unknown words. And people tested it a bit more, this inter and extrapolation performance. So interpolation is you have train and test data that's really similar. So maybe you have some e-commerce store and you have like a lot of queries and people always search for the same thing. And extrapolation is you have training data for one type of queries and then the test data is like really similar. So like because you use training data from one domain and you apply it to a different domain or language develops. And for BM25, of course, it does not make a big difference intra or like if train and test is similar or dissimilar, you always get roughly the same performance. For the cross-encoder, you also see that the drop is really small. So if train and test data is similar, or if it's dissimilar, the performance difference is kind of small. And then for the dense bi-encoder, we see like a big drop. So from 66 to 59, the performance drops extremely, showing that it does not work well if it's tested on new unknown queries on unknown topics. And sparse bi-encoders, they work much better in this respect. And this is also shown on our benchmark. So as mentioned, in domain, when we look at the dense bi-encoder and on the BM25 plus a cross-encoder re-ranker, performance is really similar. So if you have a lot of training data, both approaches perform kind of similar. But if you change the domain and you go to like biomedical domain, you see that the dense embedding model performs worse than lexical search, but lexical search plus a cross-encoder re-ranker performs much better. So this is like an interesting insight how different neural search approaches perform depending on how you use them, if you have training data or not. So cross-encoders perform really well. So why should you care about other approaches? So cross-encoders are nice in terms of like quality, but they're horrible in terms of runtime and runtime costs. So for example, if your query has like 10 tokens and your documents have 240 tokens and you want to re-rank 100 documents, and when you use a bioencoder, you just need to compute the embedding for the query. So you take these 10 tokens, you compute the embedding, and then you search in the vector space. So this takes maybe 10 milliseconds. For the cross-encoder, you have to re-rank 100 documents of 250 tokens. So you concatenate the 10 tokens of the query with the 240 tokens of the documents. And the forward pass in the transformer architecture is quadratic in the length. So encoding 250 token document takes 600 times longer. And you do this for 100 documents you want to re-rank. So overall, you have like a 60,000 times higher compute overhead if you use a cross-encoder compared to a bioencoder. And so either your search function is really slow, which no one wants, or it's really, really expensive because you have to parallelize it and like spin up a lot of GPU machines to re-rank these 100 documents. Also, an issue with cross-encoders is that you require like some first stage retrieval system. So you need to combine it with like lexical search or other search to work well. So cross-encoders, they're really good in terms of like quality, but they're horrible in terms of like costs and latency. And so we asked like, okay, how can you combine these different architectures and get a model for search that's really fast and efficient and also really cheap to run? And one way is to adapt your bioencoders to new domains. So we saw they work well if you have training data, but they don't work well if you don't have training data. So how can we adapt it? And previous methods, they did like the above flow. So they pre-train on target domain using some pre-training mechanism like masked language modeling. Then they fine-tune on some labeled data, for example, MS Marco. But this requires expensive training on the labeled source data. So for every domain you want to adapt, you have to train again on MS Marco, which has like 500,000 pairs. And in our internal systems, we have like over 2 billion pairs. So this would be like really expensive to adapt it and then to train it again on like 2 billion text pairs. So what we want is to train on these labeled data once with like the 2 billion text pairs, and then be able to do an unsupervised adaptation to a target domain. And here we proposed GPL, which combines nicely the different architectures. So you do query generation in like Dr. Query, you have some negative mining, and you have some pseudo labeling with the cross-encoder. So first you take your documents. You have your document about Python. So Python programming is a language. And then you ask a T5 encoder-decoder model to generate queries. So what could people ask? Like, what is Python? Which programming language uses indentation? How good is the readability of Python code? So these are possible search queries people could search for and would be happy to get this document as an answer. Then we do negative mining. So we take these questions, which programming language uses indentation? We check our large collection of documents about similar documents to get these hard negatives. And the final step is to use the cross-encoder to score every pair. So every query document pair is scored by the cross-encoder to tell us how similar does the cross-encoder think should the query and the document be. And to give like some real data, so this is a data set on questions in the financial domain. So we start with a document that talks about future contracts, and the model, first we generate the query so people could search for what is futures contract. And then we get the negative, like other similar passages from our collection. And some passages are actual negatives. For example, anyway, in this one example, the S&P 500 futures contract has an initial margin of. So a user would not be really happy to get this as an answer. So this would be an actual negative. However, other passages which we retrieved are not negative. So they are false negatives. So for example, here the -3 is a futures contract is simply a contract that requires party A to buy a given amount of community from party B. This would we not consider as a wrong answer or invalid answer. And with the cross-encoder, we see different relevancy scores. So the cross-encoder says that querying positive is really relevant, but also query and -3 is really relevant. So these should be all close in the vector space, should have a high relevancy in the vector space, while -2 should have a low relevancy. So we switch from this simple binary representation where we say, okay, this should be relevant and these should be irrelevant, to some more fine-grained relevancy from the cross-encoder. Then we can train the bi-encoder to learn these distances, what should be close in the vector space and whatnot. And it gives us a nice adaptation to specific domains. So here we see the initial performance. So this is the out-of-the-box model. And then the blue line is where we start to train. And the longer you train, the more it can adapt to the specific domain. And we see quite a nice improvement. So you go from 45 to 51, so 6-point NDCG of 10 improvement if you use this domain adaptation technique, and which results in much better and nicer search results for the user. The overall process of domain adaptation takes roughly 1 day on a V100 GPU. So that's roughly, I think, $75 US. So the costs are kind of reasonable to adapt the model in this way to your specific use case. So before we jump to the questions and answers, some conclusions from the talk. So dense models, they're really nice in terms of efficiency. So you can run them cheaply and fast, but they have issues with unknown words. So it's unclear how to represent them in a vector space. And one way to overcome this is you first pre-train on your specific domain, and then you fine-tune on some domain where you have data, but this is computationally really expensive. Another approach is this generative pseudo-labeling. So you use encoder-decoder model to generate queries for your domain. You use a cross-encoder to score the queries and distances in the vector space, and then you can train a bi-encoder, an efficient bi-encoder on this approach. What's still an open question mark is how can we do efficient, especially data efficient and continual domain adaptation. So our language evolves. So new entities are added every day, new companies are founded, new products are released. So how can we continually add this information to a model, which is still a big question mark. Yeah, that's so much from my side. So the code is available. So if you want to learn more about domain adaptation and how to combine these different neural search architectures, you can follow this link. And there you find examples and code and ways how you can adapt the models to your specific domain. And yeah, now I'm looking forward to questions you have.
Hello, sir. Sorry to interrupt. So before we move on to the question and answer session, I would request the audience to fill up the feedback session. So I'll be launching a poll. Please fill in the feedback poll. Hi, sir. We can go with the question and answers parallelly. Hello.
Yeah. So will you pick?
Yes, sir. Can you access this question and answer session,
yeah.
sir?
So should I just pick the first one or?
Yes, sir. Whatever questions, whatever you pick, it is up. It's your call, sir. Yeah.
Okay. So yeah, one question was on doc query. So where we generate questions for a document. And there, yeah, so either you can use some pre-trained models, so pre-trained model, for example, from MS Marco, so from search queries on Bing, Or if you have some documents where you can also create your own question, you can say, okay, this is a document here. I have like some questions people could ask or some queries people could ask and are relevant. And then you can also train your own doc-to-query model. So that works kind of, yeah, straightforward. So then it generates questions, queries, which are more specific to your specific domain. So then there's a question from Saran. Isn't cosine similarity applied only on words, or does it work well on documents? So the cosine similarity is just a function which you apply based on vectors. So it gives you a similarity between the vector. You can also replace it with like Euclidean distance. So that's the distance in the vector space, or with some dot product where you multiply these two vectors. And it's agnostic if you use it on words, or if you use it on documents, or if you use it on images. So it doesn't matter. What's interesting is like just that you have a model that goes from the document to some vector where you can use these operations in a vector space. And that's where you need the fine tuning. So if you just take the BERT model out of the box, pre-trained with masked language modeling, cosine similarity does not really work well. So the vector space looks kind of strange. And that's where we need these fine-tuning stage on the pairs, so that we get a vector space, nice vector space, where queries and relevant documents are close in this vector space using cosine similarity. So one question from is that really possible to encode a whole document, possibly be quite long, and the query using the same model? Shouldn't we focus on paragraphs or sentences? So transformer architectures, they have the issue that the runtime grows quadratic with the length of the document, so the number of tokens you have in the document. And at some point, the complexity and the memory requirement is just too big. So for the BERT network, you have a limitation of like 512 word pieces. For more recent models, it's like 2000 word pieces. And so it's not really possible to encode like a long document, like a 1000-page document, into a single vector. Here, you would use like a multi-vector approach. So you would split the document into multiple paragraphs. And then each paragraph is encoded individually into the vector space. And then instead of doing document search, you do paragraph search, and then you can map it back. So you say, okay, these are the most relevant paragraphs in my collection, and then you can map it back and say, okay, they belong to this document, and show to the user the final search results. So one question from Avinash is it okay to have only positive pairs during training? Since I have only positive pairs, I have given the sentence pair score between 4.6 to 4.9 with the above data set up, and the evaluation metrics are very low during training. So yeah, what you typically do, so you can start with just positive pairs where you have like question and answer or search query and the product the user bought in an e-commerce store. And then you just assume that if you randomly mix it with another answer, so if I take this question and I mix it with some other random question, you just assume that this is it's not relevant. And so that's called like in-batch negative. So you create these batches, and then you consider A1 and P1 as positives, and all the other P's in the batch you consider as negative, and they should be far away in the vector space. So there's one question like how to choose the proper architecture for a specific problem. So what of these architectures is the best go-to architecture at the moment? Yeah, so the best architecture at the moment is kind of hard to answer because they all have pros and cons. So if you have training data, I would say use a dense bioencoder. So a dense bioencoder works really well if you have training data. It's really fast and efficient. Also in terms of the vector databases, it's really well supported. So there are a lot of options how you can run nearest neighbor search in large vector spaces. That's like really mature space. If you do not have training data, you can generate the training data with the GPL approach I showed at the end. Or what you can try is also the cross-encoder approach. But there you need to use like a small cross-encoder, so like a 3-layer or 6-layer transformer network, which is highly optimized in terms of speed. And then you can re-rank the results from the first stage retrieval. So first stage retrieval can be lexical search, and then you re-rank the results. Cross-encoder gives you much better results, but it's a bit more expensive to run. So if you have like a small use case where you say a few users, not so much traffic, it's like fine to use the cross-encoder. But if you go like to really large use cases, like, I don't know, you're like large social network with like millions, billions of search queries per day, you want to use the dense bioencoder, and then you need to invest money how to get training data. So if you start, use the cross-encoder. If you scale, use the dense bioencoder. Yeah, the one question is about the presentation slides. So you can find all my talks on my website, nils-reimers.de. And there are all talks and all slides which you can use. So one question is like, will training performance improve the more negative samples are paired with a query? So in that example here, I only used like one hard negative. You could also add more hard negatives. There you need to do a trade-off with like the memory you have in your accelerator and your GPU. So the larger the batch size, the more GPU memory you need. So 128, you can fit it on like a single GPU. But as soon as you go over like 128, you need like a cluster of GPUs. And if so this picture is from Baidu, they have like 1,000 of GPUs. So if you have 1,000 of GPUs, you can train with larger batches. But if you're just like an individual person with a single GPU or few GPUs, you're kind of constrained with the batch size you can use. And the same thing as if you add more negatives. So each negative you add increases the requirement in terms of GPU memory. And so you need to do like a trade-off, like how many negatives can I add compared to, how large can be my batch size. And there you need to find like some optimal way to combine batch size with number of negatives. So there's a question with a batch size of 8,000. How much can they be really random with needing to mine hard negatives? So as we see here, the hard negatives training approach is always better. So if you go from pairs to triplets, the results are better because you get the negatives out of a really large collection. So out of like thousands, hundred thousands, millions of documents. So, and if you take like 4,000 random passages, it's still kind of easy to find like what's the correct answer to the original question. What we see is a certain drop of performance. For example, if you go from 8K to 16K, because then it can happen that you include like false positives, so negatives which are actually relevant to the question. And so here you need to balance, and now you also need to do certain data cleaning to actually ensure that the performance, that the negatives are actually negatives. Okay, there was like the question about the bad example and the bad negative example. So we have like these triplets, and getting the negatives, you often get them like in some automated way. So you don't create them manually, but you get them somehow automatically. For example, you look for what are you using some search function and what are like possible search results for your anchor. And if your search function finds like a negative like this, London has a population of 9 million people, you try to teach the model that A and P should be close in the vector space, and at the same time, A and N should be distant in the vector space. And it confuses the model. So why should P be close in the vector space and why should be N close in the vector space? It cannot due to semantics. So maybe it should be distant in the vector space because the negative is longer than the positive. So it tries to invent like some reasons to explain this phenomena. So to make sense of your training data. So what you really need to ensure, and where the models are really sensitive, is when you have these bad negative examples. So you need to ensure that the negatives would be actually considered by a human as a negative to the question. So it should not provide a valid answer to the question you ask. So there's a question, how does the content on beta batches with Q&A pairs reconcile with triplet pairs? So yeah, you can still do it. So if you have triplets, it's not so relevant to have like these beta batches. So because in a triplet, you would have like a question on Python, you have an answer on Python, and then some hard negative on Python. So you have still one hard negative, so one distractor, one question that's really similar to Python, but the training signal is kind of weak. So here you just have like two options which could be plausible out of your batch. And so the training signal you get is like really weak. If you have like a batch with really similar question answers and also hard negatives, you have a lot more possible answers to it, so a lot more plausible things. So the training signal is strong, which means the model learns faster and converges faster. So there's a question on the needle labor to make training examples. What we use is like basically use online sources to mine examples. So for example, we go on Stack Exchange and we get all the question and answers. You can also create this manually. There are different approaches also have different data requirements. So cross-encoders are really efficient in terms of data. So they can work well with few examples. By other approaches, they require a lot of training pairs. So for example, in these papers was tested on 200,000 manually annotated queries and documents from Microsoft Bing search engine. So this is extremely labor intensive to create like 200,000 pairs, question answer pairs. And that's why I'm specifically also interested in this unsupervised domain adaptation. So how can you take a model and make it work on your domain where you do not have any training data? So to spare you from creating like 200,000 training pairs. So there's a question to explain a bit more on cross-encoders. Sure, let me cover that a bit more. So cross-encoder, let me see. So cross-encoder uses the cross-attention you have in a transformer architecture. So you take the query, you encode it as the first segment in a transformer architecture, and then there's the document, and then you concatenate these as you have it in the Birch paper. So you take the first segment, add the separator token, and then you have the document as the second segment. And here you have the cross attention between all query tokens and all document tokens, leading to this quadratic runtime and memory requirement. And you pass it through all the layers of your transformer network. And then at the end, you take the output from the CLS token and you project it to a single score between 0 and 1. How relevant is the document for the given query? And you train it like a regression task. So you have like different pairs where you say, okay, this query and this document is relevant, or this query and this document is not relevant. And then you have the gold label, either like relevant or not relevant. And then you just train the model like a binary classifier to say, okay, this is relevant, this is not relevant. And that's how you get this model. And then you combine it with the first stage retrieval, where you get an initial set of documents. You apply this combination to all the documents. So you get like 100 documents from first stage retrieval, you compute 100 times the score, and then you rank the documents based on the score to get the top 10 output from the answer. So what's the best place to get started? Yeah, probably best place to get started is to get familiar with dense vector spaces. There are a lot of like articles online, how to use these, how to work with approximate nearest neighbor. So I would just check for tutorials or Medium blog posts on semantic search, how to apply these solutions or how to train the solution. And then depending if you more want to apply them or if you want to learn them, the answer can be different. So from Mohit, there's a question, we're using fast text solutions, training from scratch for information retrieval, and we know the capability of neural search like SBERT, and want to use this as a solution, but in some domains, pre-trained models do not perform good, and we have had to use fast text again. Could you suggest how we can use these pre-trained models? Yeah, so as mentioned, these dense models, dense embedding models, they perform kind of bad out of domain. So especially when you have like really domain specialized areas. So what I totally would suggest is to get like, if you have some spare money, to get like some annotated data. So you annotate some positive pairs, query passage pairs. And then you can train a cross encoder and a generative model, or fine tune a cross encoder and generative model. And then you can adapt the by-encoder to your specific domain. So if you have like the different scripts, runtime for this is like few days. So maybe you pay like $200 in compute. And then you get a by-encoder model that works really well for your specific domain, which is also fast, using the different architectures. So from Michelle, there's a question, when we have domain-specific text for training, is it sufficient to add a multi-layer perceptron after SBERT and only train the multi-layer perceptron, or is it better to train SBERT plus MLP? So I assume this is for classification tasks. Here, in my experience, it's better to fine-tune all the weights. So not only to train the classifier head, but to fine-tune all the weights. So there's a question from Sky, when you add more hard negatives, does that compromise the batch size itself, or do you take the anchor positive and hard negatives, include those with other observations and push through cross entropy? So yeah, it compromises on the batch size. So as mentioned, you have a limited amount of GPU memory. And if you train with like 512 batch size with hard negatives, that's equivalent to like 512. So if you train with 256 triplets, it's the same computational overhead as with 512 pairs. And that's also where we see like the dip is here like shifted. So like 4K triplets and 8K triplets is like the same performance or the same peak, where both they peak there. It has the same computational overhead. And then we see that there is like a dip, because it's like effectively you have more negatives per pair if you train with triplets and not with pairs. So from Sarvan Kumar, there's a question, how do we use some kind of model to generate hard negative examples? That's an interesting idea, if you could also generate hard negative examples. What we did instead is to mine hard negative examples. So we took the query, like which programming language use indentation. We search in a corpus using dense retrieval or lexical retrieval, and then we get these documents, and we hope that these are potentially negatives and hopefully hard negatives. And then we have the cross encoder to give us a more fine-grained signal if it's, or how relevant are these negatives to the given query. So how do dense bioencoders perform in queries that require numerical understanding? So for example, recipes that require more than 3 oranges. Yes, so numerical understanding is kind of hard, also relative things. So like, I don't know, what's the best city in Europe? This cannot really represented well in the vector space. So there the results do not often match that well. So to some simple numerical things, like I want a photo with like 2 dogs in the snow, it will give you mainly 2 dogs in the snow. But if the numerical information becomes more complex, like I want an image with twice as many dogs as cat in it and at least 5 cats, that's like too complex for a bioencoder model. Cross-encoder models, because they have the cross-attention between the query tokens and the document tokens, can perform a bit better. But in general, these models are not really that strong on numerical understanding and reasoning. So there's a question, can we use BM25 or TF-IDF as a re-ranker after getting results from sentence transformer models? Yes, you could do that, but this creates like all the issues you have with like lexical search. So if you do this and you search for what's the capital of the United States, the lexical search would be like these, you would get these search results. So it would not really understand what's in the query. But what's also became popular this year is to combine lexical search with dense retrieval. So lexical search is really good on these unknown words. So if you search for this error code, where do we have it? So if you search for this error code, lexical search is just brilliant on it, because it will find documents containing this code. And these are often documents that are relevant for you if you search for this error code. And encoder models, bioencoder, dense encoder models, they are more better in understanding and trying to interpret your search query, like what's the capital of the United States. So it will be able to interpret it, but it performs really poorly on this lexical search. And so if you combine those lexical search with BM25 plus dense encoder, you get really strong results. So that's the currently best approach. And but the challenge is in terms of like vector database, because you need to maintain and manage 2 indices. So you need to maintain an index for BM25 lexical search. You need to maintain an index for dense embeddings. And so you have like twice the overhead, how to keep these indices synchronized, how to update documents, how to leak documents. Also, the cost of running it is is double the price. So you need to check for your specific use case, is it okay to do it? So is it okay to take this additional complexity and cost, or is it better to use like some other type of approach? Yeah, that's so much in terms of questions. So. So any more questions? So if this is not the case, yeah, thank you very much for attending the seminar, and hope you learned something and can apply now semantic search and all search for your specific use case. Thank you, bye-bye.